Hi, my name is Yoni, and I'm going to talk about INT blasting. This is a joint work with all the people that are listed here. So let's start. INT blasting is an approach to reason about bit vectors, performing bit precise reasoning. And the context here is that this is done to reason about machine integers or addresses. This type of thing are most naturally translated or encoded to the framework of bit vectors. And in the theory of bit vectors in SMT, satisfiability modulo theories, we have variables that range over bit vectors. We have a bit vector constants that are represented by sequences of bits. Relations like equality, BBULT, like unsigned less than. We also have sign comparators and several operators like bit vector addition, BVAdd, multiplication, BVAnd, which is a bitwise AND operator, shift, and more. And such constraints can be combined using logical operators. All terms are sorted according to the bit width. So, for example, every variable doesn't range over all bit vectors, but only over bit vectors of a certain bit width. And in satisfiability modulo theory solvers, the state-of-the-art approach for solving these is called bit blasting. And in this approach, bit vector formulas are translated to Boolean formulas, just to propositional SAT, and then handed to a SAT solver. And then coding is done by the bits, the individual bits of bit vectors are translated into Boolean variables, and constraints are added to represent the operators and relations between them, and these are encoded as circuits. And while this is the state of the art, there are some scalability problems with this approach. For example, when large bit widths are involved, like 256, which are pretty common in smart contract verification, then this approach meets some scalability limits. And even in lower bit widths, like 32 even, then once you have multiplication or division, then also scalability problems arise because these create very large propositional formulas. This is not the only approach. There is also an approach called MCSAT and another one called local search. And in this talk, I'll talk about integer-based approaches rather than Boolean-based approaches. So translating bit vectors to integers is something that is already done in several applications. Many times it's done in the application level. For example, if you have a formula verification tool, then before sending a query to the SMT solver, the query will get translated to integers. Typically, this is done eagerly. The entire query is translated. And bitwise operators are challenging to translate to integers, and sometimes these are abstracted just to be uninterpreted completely. When you do this, then you use the SMT solver as a black box. And this approach, when you do it in your application, it's typically application specific. Other applications cannot use this encoding that you did. And what we did was to consider another approach, which is doing this translation inside the solver. This provides more flexibility. And we don't only abstract, we also do several refinement with several approaches for refinement of bitwise operations. We gain more control over what the solver is doing. And the approach is general. Any tool that uses, every verification tool that uses an SMT solver can gain from this approach. And we call this technique INT blasting, which is a translation from bit vectors to integers inside the solver. And this technique has two stages. The first is to take the bit vector formula and translate it not directly to integer arithmetic, but to an extended theory of integer arithmetic plus several operators. And then the second step is to eliminate these extended operators by transforming them to uninterpreted function. And then we get something that is supported by SMT solvers. So let's start by talking about this extension. What is this theory of integers that we call int plus INT? So this is nonlinear integer arithmetic with the addition of countably many binary operators that we call INTs, and each INT operator is indexed by a number that represents intuitively the bit width. And the semantics of INT is just doing bitwise AND. We're taking into account the number of bits in the index. So for example, if we take INT4, this binary operator, and the input for it would be 1 and 2, then the way to compute this would be to translate 1 and 2 into their binary representation, performing a bitwise AND on each of the bits, and translating it back to integers, and we get 0. And so this is the extended theory, arithmetic plus INT. Now let's see how do we translate a given bit vector formula into this theory. So the idea is this: bit vector variables are directly encoded as integer variables. We create a fresh integer variable for every bit vector variable. Constants are translated as usual as an unsigned interpretation. The operators, bit vector operators, are translated not directly to integer operators, but to integer terms. And this is based on the semantics of these operators as specified in SMT-lib. The operators that are difficult to encode directly are the bitwise operators. So bitwise AND, we translate directly to the new operators, to the INT, depending on the bit width. Other operators are eliminated. So the typical example is here at the bottom, and it would be bit vector variables, x and y. So this would be translated, x and y would be translated to x prime and y prime, and these are integer variables, fresh integer variables. And the addition is now integer addition, but this is not enough. We need to do this modulo 2 to the power of k, because that's the semantic of bit vector addition. To be more precise, we have a translation function, t, and given a bit vector formula phi, we return a conjunction. The first part is a conversion of phi, the way I just described. And the second conjunct are lemmas regarding the bounds of the new variables that were introduced. So let's go over the details here. So the conversion function C goes over the term, and depending on its shape, translate it to an integer term. So bit vector variables are mapped to integer variables, constants to constant, and equality stays equality, but the arguments are recursively converted. Similarly to equality, we have the comparators, less than or equal, etc. And we have two types of them, unsigned and signed. So for the unsigned, we just translate to the ordinary comparators in integer arithmetic. So unsigned less than would be just less than. But we also have signed comparators in bit vectors, where we check whether one argument is smaller to the other when considering them as signed in the sign interpretation. It would complement. However, our encoding is based on an unsigned interpretation. And so to handle that, we use a function that we call UTS. It's short for unsigned to signed. This function takes an integer, like 9, for example, translates it to a bit vector, and then looks at this bit vector as a signed bit vector and returns the signed interpretation as integer. So this function, if we provide 9 to it, it will return -7. And the nice thing about it is that it is definable in integer arithmetic using multiplication and modulo operator. Several other operators are done similarly to addition. We just need to do it modulo to the power of k. where k is the bit width, and for negation, there is one case where we don't need to do this. But basically, it is the same like the example I showed before with the addition. And in case, for example, here x and y are not variables, then they are converted recursively before applying this transformation. And concatenation and extraction of bit vectors, they have a natural representation in integers, and also division and remainder. However, the semantics of division and reminders in bit vectors is not exactly the same as in integers because they disagree on how to handle division by zero. So we wrap these using an ITE and if then else step. For shift operators, when you translate shift into integers, you need to multiply by a power of 2. And 2 to the power of, if we consider this operator, is not well supported in SMT solver. And so our encoding uses a case split, again an ITE, if then else. And the good thing is that the number of cases that we need is only the bit width. We don't need more than the bit width because shifting by more than the bit width results in 0. And finally, when we have a bitwise end, we translate it to INT, to the new operators that we extend the language with. And BV-OR, bitwise OR, and bitwise XOR can be eliminated to other operators using these identities. So this is the conversion function. And the only thing missing here is that we introduce several new symbols. We introduce integer variables and function symbols. We need to make sure that the range corresponds to the bit vector. So whenever we introduce a fresh integer variable, we add an assertion about it that says that it is in the range between 0 and 2 to the power of k, where k is the bit width of the original bit vector variable. And similarly for the INT functions that we add. Okay, so up to now we get a bit vector formula and translate it to an extended theory of integers. And our second step is to eliminate the extension, to eliminate all these INT operators and go back to integers and uninterpreted functions. We have two approaches to do this. One is an eager elimination and the other is lazy. So let's consider this. First of all, to eliminate the INT operator, the uninterpreted functions, but in a complete way, this relies on some axiomatization or encoding of them. And we consider two types of encoding, one that is based on sum, and this is just writing a bit vector as a sum of powers of 2, where the coefficients are either 0 or 1, depending on the specific bit. So this is the sum mode. And another mode that we have is the bitwise mode, where we compare bit by bit what we expect to have in that bit and what we actually have in that bit. And for both, we can do it eagerly by writing all these constraints right at the beginning, or lazily by starting with no constraints at all, being completely uninterpreted, and then by a Seeger loop, which is a model-based, we add only the parts that are not satisfied by a current model that we have. Okay, so let's start with the eager version. So now what the translation function is not t, it's ta, because it's parameterized by a, which is the mode, either sum or bitwise. And the input formula now is not a bit vector formula anymore, it's already an integer formula with extended operators. And what we return is the formula itself, the same formula, but with all dilemmas in advance, because this is the eager mode. And what the lemma procedure, generation procedure here does is basically traverses the formula. The interesting part is the lemmas itself. This is marked in blue. On the left side, we have I and A of the two arguments. And let's see, so if A is sum, if we are in the sum mode, then we add an equation that is based on summing the various bits with power of 2. And we need here access to the ith bit of the bit vector representation of each bit vector of each integer. But this is possible using division and modulo operators. And similarly, in the bitwise approach, we have a big conjunction that equates each bit to what we expect it to be. The ITE here encodes what the semantics of one particular bit vector and on one particular bit. Okay, so that's the eager approach. The lazy approach is basically the same, it's the same lemma, just instantiating them lazily. Plus, we add some more basic lemmas. So this is a Seeger loop. Let's see how it is set up. We start with gamma, which is a set that has a single formula, the integer plus INT variant of the bit vector formula, T of phi, but we treat all the INT operators as uninterpreted. We collect all the INT terms, all the application of the INT operator in this translation. And we have a set of lemmas that is applied on all these applications. So the first step, we check whether this abstraction, where we consider all these operators as uninterpreted, whether it is already unsat. And if it is, then it is unsat also in the correct interpretation. If it is sat, it doesn't mean that it is really sat. It may be with the model that doesn't respect the semantics of bitwise end. And so we ask for a model from a solver of integer arithmetic and uninterpreted function. And if the model satisfies all the axioms, then it can be translated to a correct bit vector model. And otherwise, we add all the lemmas that were violated in this model and continue until completion. The lemmas that we start with at the beginning are just basic lemmas, basic properties about bit vector end, for example, that it is always bounded by the two operands, it is symmetric, and some more special cases. Notice that these two modes, both of them have a usage of the SAT solver inside the SMT solver and of the nonlinear arithmetic solver. The bitwise mode relies more on the SAT solver, while the sum mode relies more on the arithmetic solver because it replaces some of the conjunctions with sigma, with sum. Okay, the next part is an evaluation. We implemented int blasting in the SMT solver CVC 5. The first part, the eager translation to the extended theory, is done in a pre-processing path. And the second part depends. In the eager mode, it is also inside the same pre-processing path. And the lazy mode is done in a specialized solver that implements a Seeger loop. For the evaluation, we compared these approaches that we implemented with other tools, Bitwutzla, Yikes, and the default bit vector solver of CVC5. And we consider three classes of benchmarks: the SMT-lib, QFBV family of SMT-lib, some handcrafted rewrite rule candidates for the theory of bit vector, and most importantly, for this meeting, smart contract verification benchmarks that we got from Certora. So let's start with the first set from SMT-lib, the QFBV family. This is a quantifier-free bit vector-only formula. This is a very, very large family and very diverse. However, it doesn't have a lot of large bit width in it. And in this family, our approach, the int blasting approach, is not very competitive. Bit blasting performs much better. We can see it on the left column. The top parts are the int blasting approaches, and the bottom are the bit blasting approaches. We can see, however, that for unsat formulas, this is the third sub-column, for unsat formulas, this approach comes closer to being competitive than the SAT in the SAT case. Okay, so that's the SMT-lib family. Another evaluation that we did was with rewrite rule candidates. And for that, we really wanted to test how this approach in blasting performs for formulas as the bit width increases. And we wanted control over the formulas, over the bit width of the formulas. And so we crafted rewrite rule candidates for SMT solvers. SMT solvers use many rewrite rules that are just equalities between bit vector terms. So what we did is that we automatically synthesize pairs of terms that are equal or equivalent for bit width 4. And then we wanted to prove their correctness, their equivalence for larger bit width. And so after we synthesized them, we synthesized over 5,000 of these pairs. We instantiated each pair with 10 different bit widths, starting from 16, going with power of 2 all the way to 8,192. And we got 10 bits. So overall, we got a lot of benchmarks this way. And with this set, the int blasting approaches, all of them are better than bit blasting. And the best configuration for int blasting was the lazy one with the bitwise encoding and not the sum encoding. Let's see some more details about this evaluation. So if we consider the rewrite rule candidates that involve the BV-end operator, then we see that the in-blasting approaches that are the red approaches, if we look at the best one, the top one, the triangles, then starting from bit with 512, and this approach becomes better than the bit blasting approaches. And another nice thing about it is that the performance is relatively bit width independent for this approach. We see that bit blasting approaches go down as the bit width increases, while this is almost a constant line in the in-blasting approach. Now, without bit vector end, for rewrite rule candidates, pairs of equivalent terms with no BVN, all our four approaches are the same, and they become they are bit width independent empirically, and they become better at 128 bit width. For the full set, it becomes better at 256 bit. The last set of benchmarks is from Certora. We got 35 benchmarks from them. These are QF, UF, PV, uninterpreted functions, and bit vectors, no quantifier, with 256 bit vectors, and they employ both arithmetic and bitwise operators and encode algebraic properties of low-level methods. And also in this set, the in-blasting approaches were better, both in terms of how many benchmarks were solved. They solved more benchmarks than the other approaches, and also in speed. They were much faster than the other. Okay, so here I'll conclude. We've seen an approach for solving bit vector formulas, especially for large bit widths, and the motivation here was formulas with large bit widths, especially coming from smart contract verification. We see that it is not completely competitive in general to bit blasting, but can serve as a complement to bit blasting. We've seen 4 different configurations with either eager or lazy and 2 types of encodings. And yeah, we've seen that it is good in several cases for large bits. In the future, we plan to work on abstractions of other operations. Here we worked on BVN, but the next challenge would be shift operation. Consider more benchmark, and any improvement in a nonlinear integer arithmetic solver will immediately have the immediate potential to improve this approach because of the translation. And that's it. Thank you.
Yeah, so I saw that when you were implementing like integer and or these integer bitwise operations, you would break them down to bits by using integer division. Have you explored how that compares to defining it more implicitly by saying, you have n variables that are either 0 or 1, and these, added by powers of 2, give you the original integer, or do you find that the division way you did it ends up giving better performance?
Well, if you do it with variables instead of using the divisions, then how do you relate these n variables to their origin?
Yeah, so like for like one 32-bit integer, you would I think like you create 32 variables that are each, constrain them to be 0 or 1, and then you use a sum to say then this equals that original value a.
I see. Well, no, we didn't do it. We didn't consider this. Instead of variables, we have terms, but in addition, well, for better and for worse, we have more data on them, right? Like we know exactly what they are. But yeah, it could be interesting because division and mod are a bottleneck in the arithmetic solver. So this might be a way to overcome this. So that's an interesting
Yeah,
direction.
you could also add them in addition to what you have without affecting the correctness. Right? Yeah.
Yeah. Thank you.